Today we're going to try and talk about moments and how to solve simple moments problems. So sometimes we find when a force acts that is trying to cause something to turn. For example, if we push down on the spanner here, we would expect the spanner to turn in this direction. So sometimes a force is trying to make something turn or rotate. And that turning effect is called the moment. So we say that this force is causing a moment. Now, like all things in physics, we try to apply numbers to this, and the moment will have a strength, and the strength of a moment will depend on the size of the force and what we call its perpendicular distance from the pivot. Basically, perpendicular means that it's at right angles to the line of the force. So there's sort of a right angle between the line of this force and the distance we're measuring. And we measure to the center of rotation, and we call that the pivot. So the center of where the spanner can rotate about is called the pivot. And we're always interested in how far that force is from that pivot, because that's what gives us the strength of its moment. So how do we find the strength? Well, the strength is found simply by multiplying the force by its distance from the pivot. So to make that into a little equation, we say that moment equals force times distance, where the distance is the perpendicular distance at right angles to the line of the force. So moment is force times its distance from the pivot. Now rotations have directions. In this case, this force is causing the spanner to rotate, and it's rotating the same way the hands of a clock would move. So we call that a clockwise moment. And as I say, that's defined because the thing is trying to move the same way that the hands of a clock would turn. So we say that this force down on the right hand side here, or you'll see that you get the same behavior if you're pushing up on the left. So up on the left, down on the right, both create what we call a clockwise moment. Now if we push up on the right, or indeed down on the left, we create the opposite moment. And because the spanner is now moving the opposite way to the way the hands of a clock would move, we call that an anticlockwise moment, because the force is trying to move the spanner the opposite way to the way the hands of a clock would move. So we call that an anticlockwise moment. And you can see if you're pushing down on the left, you create an anticlockwise moment. And if you're pushing up on the right, you're creating an anticlockwise moment. Let's try a simple example of calculating a moment. Let's say we had a force of 30 newtons pushing at a distance of 20 centimeters from the pivot. That would look something like this if it was a clockwise one. And so we have an equation for moment. That moment equals force times distance. And then we just put in our values. 30 newtons for the force, 20 centimeters for the distance. Always put them in the order they appear in your equation so that you can check your work more easily later. And we get a value of 600. But what would the units be? Well, we multiplied some newtons by some centimeters. So that's what the units are, newton centimeters. If you multiplied newtons by some meters, you would get newton meters. If you multiply some newtons by some millimeters, you would get newton millimeters. So it's always going to be a force times a distance, because that's, remember, our equation is a force times a distance. We would expect the units of the answer to be in force units times distance units. So when we show a method, we put in our formula or equation, then we substitute in the order they came in, then we get an answer when we multiply them, and then we add a unit based on what units did we multiply. In this case, we multiplied some newtons by some centimeters, so we get newton centimeters. Formula, numbers, answer, unit. And if you keep a structure to your work, you'll find that this kind of stuff is much easier than if you go a bit more haphazard with your working out. So try and keep a nice clear structure to your working out. So what if at a certain distance out from the pivot we had a certain value of force? Now that's going to create an anti-clockwise moment, trying to turn this rod, which is balanced before we touch it, trying to turn this rod anti-clockwise. What if on the other side we had, at a particular distance out, another force that produced an identical size of clockwise moment? Would that not stop the rod from turning? And so the idea here is of something that we call the principle of moments. And it's basically stating that if the total clockwise moment has the same size as the total anti-clockwise moment, that we wouldn't expect the thing to turn. Or flip that on its head, if the object is not turning, then the total clockwise moment must equal the total anti-clockwise moment. So the statement of the principle of moments is that for an object in equilibrium, in other words balanced like this, the sum of the clockwise moments about a point must equal the sum of the anti-clockwise moments about that same point. So in our case the point is the pivot. So what this shows is that a big force at a small distance can counteract the moment of a smaller force at a bigger distance, and vice versa. So the principle of moments can be written as total anticlockwise moment equals total clockwise moment. So if this system is balanced, this equation will be true. Some people just write a shorthand version like this, and some people do it in symbols, because if you name the pivot, you can write it in symbols like that. Either way, you then have to start filling in the moments. So in the above problem, we have F1 causing an anticlockwise moment at a distance d1, and F2 causing a clockwise moment at a distance d2. So we say that F1 times d1 must equal F2 times d2. And this problem would come up in such a way that out of these four things you know three of them, and you're being asked to find one. Let's put some values onto this problem and see if we can solve for the missing bit of information. So let's make F1 12 newtons and D1 30 centimeters and F2 6 newtons, and so in this problem we'll be expected to find D2. So the 12 newtons is trying to create an anti-clockwise moment, and the 6 newtons is trying to create a clockwise moment. So we can say if this is an equilibrium, if it's balanced, then the anti-clockwise moment must equal the clockwise moment about the pivot. And we can write that in symbols like that. Now we need to fill in this anti-clockwise moment. Moment is force times distance, so 12 newtons times 30 centimeters. Always fill them in the same order, with force first and distance second. And then we can do that for the other side. We don't know d2, but we can write it as 6 times d2. Now we want d2, but we've got 6 times d2. The correct thing to do is to divide both sides by 6. And so we can now just put that through our calculator, and that gives us D2 equal to 60 centimeters. So that's how we would find an unknown distance. We start by adding all the numbers to the problem. If it's described to us, we would draw it out. We then say that the total anticlockwise moment has to equal the total clockwise moment. Then we fill in the anticlockwise moment. This is trying to pull it anticlockwise, so it's this force times this distance, 12 times 30. And then on the other side we've got 6 newtons times an unknown distance d2. And then we have all our moments. We then solve this by getting d2 on its own, dividing by 6 here, divide this by 6 to get this, divide this by 6 to get this, and then just putting this through the calculator, you can see we get 60. So in this problem we're asked to find an unknown force. We're given F1 and D1, and we're given it D2 this time, but we don't know F2. So again, we can only solve this when it's balanced, because that's the only time when the moments are equal. So we assume that it is balanced in a problem. So again, if it's balanced, the anticlockwise moment about P equals the clockwise moment about P. Now the anticlockwise moment is going to be what's happening with the F1 and the D1 here, and the clockwise moment is going to be what's happening with the F2 and the D2. So we just fill that in. Some people like to write it in symbols first before they put the numbers in. And so 20 times 10 equals F2 times 40. And again, always put them in the order of force times distance, the way you would in a normal, just finding a normal moment. Moment equals force times distance. If you've learnt it that way, always put them in the order that they appear. So 20 times 10 equals F2 times 40. We need to divide both sides by 40 to get F2 on its own. So we get 20 times 10 over 40 equals F2. And 20 tens are 200, and 200 over 40 gives us F2 equal to 5 newtons. And we can just check that the moments are balanced, because 20 times 10 here is 200, and 40 times 5 is 200. Sorry, 5 times 40, if you put them in the correct order. So the moments are equal, and they have to be for it to be balanced. So that's the only two things you can be asked to do in a moments problem, is find an unknown force or find an unknown distance. You have to know all the other values. Okay, so this is an actual exam question, and the problem with actual exam questions is that they don't set themselves out nice and straightforwardly for you to do your moments calculation. They give you all the information you need, but you have to root around in the detail of it in order to figure out what it is that you're trying to get. And really what you want to do here is go from what they've shown you to a nice simple diagram that you can do the moments calculation from. So it says the wooden rod has a length of 1.4 meters and is suspended from a stand by a length of string attached 30 centimeters from end A. He moves the 2 Newton weight until the wooden rod is balanced horizontally, and the 2 Newton weight is 10 centimeters from end A when this happens. So this is the situation when it's balanced. The most important thing to do here is to recognize that the pivot is where it's hanging from the string. That is where the pivot is. So the only distances we're interested in are distances from that. Okay, so firstly, the 2 newtons, if it's 30 up in the top part there, this must be 20. Because if we've got 30 here, 10 here, there must be 20 here. So the 2 newtons is 20 from the pivot, but where's the weight of the wooden rod itself? Well, we're told that it's a uniform length of wood and it's 1.4 meters long. So the weight will act from the center of gravity, which will be in the middle. And the middle is going to be 70 centimeters from the end, which means this must be 40. So now what we do is redraw this with the pivot here, with our 2 newtons here, and that's a distance of 20, and a distance of 40. We have the weight of the rod. And now we have a simple problem that we can solve. So we can now find this weight here by solving this moments problem. And we've got an anti-clockwise moment about the pivot of 2 times 20 and a clockwise moment of W times 40. So if it is balanced, and they've told us it is, then they must be equal. So anti-clockwise moment about the pivot equals clockwise moment about the pivot, which means that 2 times 20 equals W times 40. And so we need to divide both sides by 40 to get W on its own, and that means that W must equal 1 Newton. So the weight of the rod of wood is 1 Newton. So this is a problem from an exam paper, and it has this steam pressure valve. You can see that there is steam coming up here, pushing on this little plug, and there's a weight here. And I'll try and explain what's going on for those of you who can't see how this works. So I've opened the thing up a bit so that you can see the weight acting. So the weight is acting here, trying to pull this down. The steam is pushing up here, trying to push this plug out. And the two things are in equilibrium. There's an upward force here, creating an anti-clockwise moment. There's a downward force here, creating a clockwise moment. And the two of them are in equilibrium. So that's really what's going on with this device. Some people looking at this picture couldn't really see what was going on. So there's essentially an upward force here, a downward force here, and so we've got a clockwise and an anti-clockwise moment, and we've got obviously as well a pivot here. You have this steam force then that we'll just call F pushing up, and we have obviously the 25 newtons pushing down. So the 25 is trying to create a clockwise moment, the F is trying to create an anti-clockwise moment, and at the point we're interested in, these are in equilibrium. Now, the most common problem with this question was people using these two numbers with the two forces. So F times 5 is fair enough, that is the moment about the pivot. But the 25 times 30 is not the distance to the pivot here, because the pivot is actually 35 centimeters away from that weight, and that is the distance we need. So this is where remembering the definition of the moment value and how you calculate it, that the moment is the force times its perpendicular distance from the pivot. So when you do any moments problems, you should always be carefully identifying the pivot and how far each force is from that pivot. And I have been stunned at the number of students who have made this mistake, not once, but twice and sometimes 3 times, when they had come across this question multiple times and every time used the 30 instead of the 35. And this is why I always recommend that you redraw a moments problem with only the information that you're interested in on it before you start doing the calculation. So here I've separated out the upward force, and it's 5 centimeters from the pivot, the 25 down and the 35 centimeters from the pivot, so that they are completely separate to the original diagram. It makes it much easier to do the moments problem. So now we just have to think about the moments either side of that pivot, clockwise and anti-clockwise. So anti-clockwise moment about the pivot equals clockwise moment about the pivot. F times 5 is the anti-clockwise, and 25 times 35 is the clockwise. And I'm a bit short of room here, so I'm going to have to go sideways. We need to divide by 5 to get the F on its own, so we need to divide the right hand side by 5 as well. And that gives us an F value of 175 newtons. So it all comes down to remembering that it's force times distance from the pivot, not just any old distance. The people that kept making the mistake with using this number, this is a standard old trick that they put information in that lets you find the right numbers, but it's not just a straight plugging in. You have to sometimes root around for the numbers you're after. So be careful when you're doing these problems.